was that in the context of any machine learning algorithm, there are two types of errors that you can measure. Okay, so one of the error is called it's 21st today, 22nd, yeah. All right. So there are two types of error. Okay, one error is what we call training error, right? Which is whatever your model is, how much, what is its error on the training data that you already have. All right. So that is something that we can measure. That's easy to measure, right? The other error is what we call, sometimes we call it testing error, which means that once you have trained the model, now you are testing it on some other data, the data that you never exposed to the model during the learning phase, right? So that's called the testing error, or we also call it the generalization error, which means that after training it, when you apply it in a general outside, how well does it do, right? Now, what we really want is a model that can do very well on the testing or the generalization error, right? Because anybody can do well on the training error, but what is more important is to have a model that can do well after the training, right? Unfortunately, training error is what we usually optimize on, right? If you remember your neural network or perceptrons, we are trying to minimize the training error. Why? Because that is something that we can measure, right? We cannot measure the testing error during training because we do not have the test data, right? In general, it's not possible to have the test data beforehand, so it is not easy to come up with methods that can sort of minimize that, right? This is the only thing that we can minimize. However, what we want is this. So there is a sort of this situation here, which is that we can only minimize this, but what we really want is a model that can have a low error, right? Okay, so first let us look at how to minimize the training error, right? So let's say this is just a hypothetical plot where this axis is error, right? Now, one way or the way to minimize the error is by making your model more and more complex. All right. So, for example, and for illustration, let's say you have two types of data points, right? And you're trying to distinguish between them. Right. If I only draw a line, right, a straight line, I might not be, I would do fairly well, but not perfect, right? However, if I make it a quadratic curve, I might do a little better, right? And if I keep making my curve more and more sort of complex, what you will see is that you can always draw a curve which eventually does distinguish between the two types of points, right? So what happens is that as you increase the complexity of your model, or as you increase the complexity of your hypothesis space, right? So instead of just looking for lines, let's look for curves. As this increases, what you will see is that your error will go down. And the exact curve might be different, but that's kind of the general behavior, that as the complexity increases, now this is the training error, right? The training error would go down, right? In fact, for neural networks, as I said, you can always come up with a neural network that would give you zero training error, which means that it will do perfectly on your training data. However, that's not what we want, right? So the next error we talked about is the generalization error, right? So what happens with generalization error is that, of course, when your model is very simple, your generalization error would also be pretty high, right? Because it's probably here. But what typically happens is that as your model becomes more complex, your error goes down, but after a point, your error starts increasing. All right, so this is generalization error, which means that even though by making your model more and more complex, you would come up with a model which has zero training error, but it doesn't guarantee. In fact, it works in the opposite way. Your model will become poorer and poorer in terms of the generalization error. So, right. So this area is what we call. So sometimes we also refer to this as overfitting. This phenomena. Right? You say that okay, this is where your data is sort of believing that. Oh, sorry, your model is believing the training data too much, right? And hence it might not do very well. All right. So essentially what we need is a sweet spot over here where you would guarantee that not only your training error is not too high, but your test error is also the minimum. In fact, you do want that, right? You always want a spot where your testing error is the minimum. All right. So this notion is, so what we say is that any model that is over here, which is very less in complexity and giving high training error, this is what we call a model with a high bias and low variance. All right. And the model which is over here, this is what we call low bias and high variance. And I'll tell you why these are called these words. This, don't confuse this with the bias that we have looked at. That's more of a geometric concept. But this is, in the machine learning language, bias and variance trade-off. All right. So think about bias and variance like this. So let's say there's a person, right? And you will see people like these often. So there are two types of people. One person is one who sort of changes his or her opinion every day, right? So let's say here's a person who is trying to see who to vote for the, Republican presidential nomination, let's say, right? So let's say there are 6 options. Every day, this person gets the news, some information, and changes his or her decision. Says, okay, today I'm going to vote for person A, tomorrow B, next day C. And on the other hand, there's another person who never changes his opinion. Always says, I'm going to vote for person A, right? Even though tomorrow it turns out that this guy is a murderer, but he would not change his opinion. So this person is a person who has a very high bias. He doesn't change at all. And the other guy who keeps changing his opinion is a person who has very high variance, right? The reason we call it variance is because the model changes a lot every time you change the training data, right? So for example, let me redraw it. But let's consider this example again, right? So let's say these are some of our positive points, and these are some of my negative points, right? A model which has a very high variance, what it would do is, it would try to learn a perfect curve which distinguishes this, right? However, if you take a slightly different training data, right? So for example, in your assignment, let's say you take a different random sample in which the general behavior is the same, but of course the points are different. What will happen in that case is, now it will change a lot. The model will be very different. All right? These two models are very different. So that means that this learning algorithm has a very high variance. It changes a lot with the training data. Whereas you could have had another model which learns a line. So even if the data changes a little bit, this line would still be the same, right? So this model has a very high bias, right? It sticks to what it thinks is true, and it doesn't change itself too much, all right? So in this curve, this is how you sort of straddle the spectrum. So you start here you have the highest bias and lowest variance, and you move this way, your bias goes down, but your variance goes up. Now what we want to, the place where we want to be is somewhere here, optimal, right? So not too much, so because you can't have an algorithm which has very high bias and no variance at all, which means that even if new information is coming in, it does not learn from that. So it does not learn anything from the training data, right? And on the other hand, the overfitting example is easy to understand, which is it sort of keeps changing as new information comes in. So you want to be somewhere in the middle. You do want to learn from your training data, but you also do not want to sort of overfit on that training data. All right? So that's the concept of bias variance trade-off. In the context of machine learning, this is very important. It means that every machine learning algorithm should have two properties. It should have one way to minimize your training error, because that's something that you can calculate, but at the same hand, at the same time, it should also have a capability of addressing this bias variance trade-off, all right? Which means now we have seen that this complexity of a model has a direct relationship to this, which means you do not want too complex a model. If your model is too complex, you would be somewhere here, but you also don't want too simple a model, so you want somewhere in the middle, right? There is a whole week of material that I kind of skipped in the interest of time and continuity, where we talk about, and maybe we can come to that later on, where we talk about how to actually measure the complexity of an algorithm, all right? So in general sense, there is something called a VC dimension, which is like a value that you assign to a model or to a hypothesis space, right? Which kind of measures the complexity. But now we will see what does it mean, what is the complexity of a neural network? So in general, for any machine learning algorithm, if you tomorrow go out and say, I'm going to create a new machine learning algorithm, right? The first thing you want to understand is, of course, what is the training error and how do you minimize that? But also, what is the complexity of this algorithm, all right? And then you can sort of control it somehow. So in the context of neural networks, it turns out the magnitudes of the weights. So remember that in a neural network you have many units, output and hidden. Each unit has a weight vector associated with it, right? So it turns out that the magnitude of all these weights is directly proportional to the complexity. If these weights are very high, it means that your model is very complex, all right? Why is that so is something that you can understand more from a geometric perspective. So maybe 3 weeks later when we do regression, I'm going to talk about that. But the general idea is this, right? So what a neural network also does is it kind of draws these curves, all right? So if you take a two-dimensional example, you learn a neural network, what you will see is that the effect that it is having is that it is trying to partition your data, your training data, into these regions, right? Now, so which essentially means that those weights in the hidden and output units affect the sort of the complexity of this curve, right? And if you keep these weights very low, it would mean that it would prefer sort of straighter boundaries between these different regions. However, if you keep the weights high, they would be more complex, right? So which means that if we can control the weights, we can keep our solution less complex. Yes? Right. Yeah. So the question is, why is that so, right? Why do we say this? So again, let me give you a simpler example, and then it generalizes, right? So think of a perceptron, right? A perceptron tries to learn this line, W transpose X equal to 0 or theta, or let's say 0. Let's assume that there's a bias already here, right? Which means, and this W essentially controls the weight, the line, right? So depending on what W is, your line would be like this or like this or like this, right? Now, what a neural network does is that it generalizes this line, right? Now, instead of lines, it's saying here is a curve. This curve is parameterized by these weights in the hidden and output units. Now, what you will see is if all of your weights are very high, so you can think of something like, let's say, consider any weight vector, any hidden, let's say this is the hidden unit, okay? So this is weight 1, 1, weight 1, 2, weight 1, 3, and so on, right? If these weights are very high, what will happen is that the effect of these, because all of these weights get multiplied with your input vectors, right? At least in the hidden unit, and then so on. If these weights are very high, they get multiplied with these input values, and then that produces the result, right? So if I change this x a little bit, the effect of changing this input a little bit will have a large impact if it is getting multiplied by a large value, right? Because let's say this is x1, right? So the effect of this weight is w11 times x1, right? Now if I change my x1 by delta x1, it becomes x1 plus delta x1 times w11, right? So the extra impact of this is higher if my w11 is high, right? So if you want to control the effect, because if you want to keep your variance low, right, you don't want to get too much influenced by training examples. So that w weight tries to control that, all right? So however, there is also a geometric interpretation, but I don't want to give it right now because we need to sort of understand linear regression, and then we'll do that. But in general, this is sort of the idea. You do not want very large weights, because larger weights means that the influence of training examples becomes very important, all right? However, if you have, so let's say w11 is 0, right? In this would have very high bias. Why? Because whatever the value of x1 is, it will not consider it at all. So that's sort of the intuition. All right. So how to control it is actually pretty easy. So what we do is, in order to control the magnitude of weights, we introduce a new error function, which is the error function that we have seen in backpropagation already, which is essentially the squared error, right? So this is I equal to 1 through something, p equal to 1 through n, half I equal to, L equal to 1 through k, y p L minus OPL whole square, right? So this was the training error, right? But we add another part here, which is essentially the summation of squares of all weights. So I'm just going to write some index here. But think of, so remember, there are two sets of weights here, hidden units and output units. So essentially what you do is you sum up all of their values, all right? Square them and sum them up because you want to minimize their magnitudes, and this plus lambda, right? So this is penalty on the weights. And lambda is a scalar value that we introduce to control what you want more, all right? So I'll come to that, all right? So essentially what's happening is that if we didn't have this, right, then we would prefer a solution. We would prefer weights which minimize this, right? But now by adding this, what we are saying is that not only do we want to minimize this, but we also want to make sure that these values are not too high, right? So if you had a solution in which this was 0, but these weights are very large, then the total error would still be high, right? And there might be a different solution in which the training error might be a little more, but this might be low. So it would prefer that, right? So this is a way to control the magnitudes of these things. So this procedure in general is also known as regularization, right? So we are trying to regularize or regulate the solution. We are trying to keep it simple by introducing this penalty term. And this itself is a huge area of research. Yes, go ahead.
I can't see whether this is the parenthesis.
You can't see, oh, this part? All right. So, well, I was trying to be a little lazy, but essentially what this is well, okay. So remember that in neural networks, last time I said that we have two matrices, right? W1 and W2. W1 is all the weight vectors in the hidden units arranged in a matrix, and this is all the weight vectors arranged in the other units, right? So what this is it's taking every entry of both of these matrices and summing them up, squares of them. So it's basically the total sum of the weights. So by introducing this term, we are trying to move towards solutions which not only minimize this but also keep it simple. So essentially, we are trying to reach somewhere here. See, if we didn't have this part, we were trying to be here, right? We are trying to find the solution which minimizes the error, but now we are trying to move towards the right. So that's called regularization. All right. So in your assignment, you have to draw this curve, right? So you'll see the part two of the assignment. You need to draw this curve because what I tell you is you basically try to compute these errors for different complexities. All right. Now there was one more parameter that I didn't talk about much. Is this lambda? Okay. Now lambda is a value. Lambda is typically between 0 and 1, and that controls how much you want to put emphasis on simplicity and how much on low training error. So if we set lambda to 0, then that means that you want a solution which has very low training error. If you set lambda to very high, that means that well, lambda can be anything actually. So that means you're preferring more sort of simpler solution. So in some sense, in that case, lambda essentially is this complexity parameter, right? So if you keep lambda, well, it goes the other way. But if you keep lambda to be very low, then you're trying to be here. If you keep lambda to be very high, you're trying to be here. Unfortunately, there is no principled way of knowing what lambda is. All right. So lambda is something that you set. So it's kind of like a hyperparameter. You set it. There is no way to learn it from the training data. All right. So in the programming assignment, what I ask you to do is try out different values of lambda, starting from 0 or very low to very high, all right, and see what behavior you get. All right. Any questions so far? Yes.
If lambda is zero, what about for something further small training or
You, right. Actually, yeah, you're right. Sorry, yeah. So lambda 0 means you're here because you're emphasizing on low training error. And lambda higher is means you're here. So the curves that you might get might be reversed if you order it by lambda, right? But the general idea is that lambda helps you control the complexity of your algorithm. Any other questions? Fantastic. So that ends our discussion on neural networks and regularization. So now what we will do is we'll start a new topic in the general area of statistical machine learning, right? Or probabilistic machine learning. Right? So this is a different way of looking at of doing machine learning, right? The quick the quick introduction to this is that see, so far we have been looking at more of these geometric or functional methods to do machine learning, right? We assume that the output y is some function of the input x, and then we try to learn that as a neural network or as a perceptron or as a conjunctive hypothesis. However, and many of you also raised those questions in the first week, is that there are no guarantees that the training data that you're getting is correct, right? There could be a lot of randomness in the data. So probabilistic machine learning methods or statistical methods explicitly model those randomness. All right. So I'm going to do that today. Well, so what we will do is today and half of Wednesday we will sort of look at basic concepts of machine learning and probability and statistics, and then we will move on to how to use it for machine learning. But I would encourage all of you to go through these slides on your own. I'm sure a lot of you know a lot of these things already, but just as a refresher, just go through these so that you're aware of all these concepts. All right. So the first question is, what is probability? And I'm sure all of you know that, right? So, for example, we often say that probability that when I toss a coin, the probability of observing a heads is 0.5, right? Which means that probability that a coin will land heads is 50%. However, there are two different interpretations of this. Like how do I interpret this probability, right? So there are two schools within statistics who interpret probability in different ways, right? One of them are what we call frequentists, and one of them we call Bayesians, right? And the reason I show it like this is because oftentimes they kind of are, against each other, or the way they interpret other things as well are different. So there's a lot of, I wouldn't say tension, but there is some difference in opinion in the way they look at probability, right? So what is the frequentist interpretation of probability? It means that when I say that the probability of an event is something, it means that if so let's say I say that the probability of a coin toss is 50%, it means that if I toss the coin 100 times, then it's likely that 50 of those times it will be heads. So that's how frequentists sort of interpret that probability, all right? But there are some issues with that. So for example, what if my event is something that I cannot try many times? For example, an Armageddon or a meteor hitting the Earth, right? So if somebody says the probability of a meteor hitting the Earth is 0.1, I cannot take multiple trials of that, right? Unless we sort of live in if we believe in sort of multiple universes, and then you can say, okay, if we do it in every universe, right? But the general idea is that the frequentist interpretation breaks in the context of events that cannot be done multiple times, right? So then comes this other interpretation, which is Bayesian interpretation. So Bayesians, the way they interpret probability is that they associate it with the uncertainty of the event, all right? So when I say the probability of a coin toss and getting a heads is 0.5, then they say that the certainty of it being heads is 0.5. So it's just two ways of interpreting the same thing, right? The way they use it is, it becomes then understand how to use probability. For example, if somebody says, the probability of me winning a lottery is 70% today, then if I go and make an offer on a sports car, then that's the amount of sort of tension, or what should I say? My heart rate would be up by that much, right? So if somebody says the probability of you winning a lottery is 90%, I would be much more calm when I'm going to buy a sports car. If somebody says it's 5%, then I probably am a little more scared, right? So that is the Bayesian view of things. But that's not the only way Bayesian and frequentist statisticians differ. There are many other things as well, and we will come to those later on, all right? However, something that is unique to both is the notion of a random variable, all right? So so random variable is something that you observe, all right? So for example, the temperature of Buffalo tomorrow is something that you will observe tomorrow, right? Now it could be anything, right? It could be 20, it could be 25, 35, it could take any of infinite values, right? So that is what we call random variable. So every random variable has a domain, right? The values that it can pick from. For example, so we can define two types of random variables. One is a discrete random variable in which the domain is finite. So for example, the color of an object, right? So the color of an object, so let's say you have a jar full of balls of 4 different colors, red, blue, green, and orange, right? So every time you close your eyes and you stick your hand in the jar and pick out a ball, it could be of any color. You don't know that, right? Because the balls by touching are identical. So, but it can only take one of the 4 values, right? It could be red, blue, green, or orange, which means that it is a discrete random variable. It's random because it could take any of those 4 values, but it is discrete random because it can take only one of the 4 values. However, if you are looking at something else, like let's say, as I said, temperature can take infinite possible values. So it will be random, but it would be continuous. All right. So we typically associate a probability with that random variable taking a value. All right. So when I say P of X, because probability is always associated with an event, right? Probability of a coin toss. It's not the probability of a coin, but it's the probability of what you observe when you toss a coin, right? So probability is a general notion, but in the context of random variable, P of x equal to x means that this random variable x has the value small x. So for example, what is the probability that the temperature tomorrow will be 35 Fahrenheit, right? In this case, the random variable is temperature, right? And that is capital X, and the small x, the lowercase x, is the actual value, right? Sometimes we, just to be sort of concise, we often write P of x, which essentially means that we are assuming that x is already there, the uppercase x, and then we are essentially saying what is the probability of uppercase x equal to x, all right? Any questions so far? Okay. So as you have seen earlier as well, that with generally with machine learning, notation is very key, right? And again, here also, unfortunately, because probability discipline or statistics is sort of a different discipline, machine learning is a different discipline. So what has happened over time is that everybody has adopted their own notation. So I'll again try to be a little consistent, but correct me if you see somewhere I'm deviating away, right? So we typically use an uppercase normal regular x as a random variable to denote a random variable. If your random variable itself is a vector, right? So far I said, okay, temperature, that's a scalar value. Color, that's a categorical value. But it could also be a vector of observations, right? So then we denote it by a bold x. A, a lowercase x is used to denote a specific value. So red, right? And then P of x is that event. Then okay. All right. So then I'll come to these functions later. All right. Then there are some basic rules. I don't want to go through these too much, but there's a notion of joint probability. There's notion of, so if you have two random variables, the joint probability is essentially what is the probability of observing both of them together. Uh, these are two events. So random variables would be x equal to y. So for example, let's say you have two random variables, x and y. Then what is the joint probability of x to be small of x and y to be small of x can be written as this. There's a notion of conditional probability and all of that. I'm assuming you all know that. There's also this notion of breaking up a joint probability distribution as this. Actually, I already made a mistake here, right? So essentially, this should be x1 equal to small x1, x2 equal to small x2. All of this can be broken up like this. So this is what is called the chain rule of probability, right? There's also a notion of marginal distribution. So if you have two events, right, then you can compute the marginal distribution of only one event by summing over all other possibilities, right? Also known as the sum rule. All right. And then there is the most important part that you need to be very clear on is what is called the Bayes theorem, right? So if you have two random variables, x and y, and x takes small x is one event and y takes small y is another event, then this conditional probability can be also computed like this. All right. This comes from the chain rule, right? Then this gets broken up because of the marginal distribution, and this is what you get, right? I'm assuming you all are familiar with that, but please refresh your sort of understanding of this. Especially, you can look at this example to refresh it a little more, all right? Let's see. All right. So let's look at this example. So let's say you have two random events, all right? you have one random event which says a test, some medical test, is positive or negative. So let's consider a random variable, capital uppercase X, which essentially denotes that when I go for a medical test, if it comes as positive, then X equal to 1. If it comes negative, X equal to minus 1. So this is a discrete random variable, of course, because it takes only two values. And here is another random event, which is denoted by this random variable Y, which says, does this person have cancer or not, right? It can take two values, all right. So let's say you know these things. Let's say you know that the test has accuracy of 80%. Now, what does it mean in terms of conditional random variables? Is that, well, it's always already here. So 80% means that probability of x equal to 1 given y equal to 1 is 0.8, right? 80%. Because x equal to 1 means that this person has tested positive given this person actually had cancer, right? So that kind of is the accuracy of this test. So if it's a good test, accuracy will be very high. If not, it will be low, right? The probability of test to be negative given that the person has cancer will be 0.2, right? The p of x equal to 0 given y equal to 1 is 0.2 because those are the only two possibilities, right? So that's easy. Let's say you're also given this. This is prior probability of having cancer. So before anybody enters hospital, what is the probability of that person to have cancer, right? That's often called the prior probability. That's something that you already know about that disease, right? Without having looked at the patient at all. So let's say in this case, that probability is 0.4%, which means that probability of y equal to 1 is 0.004, right? My question is that if I test positive, if I go get the test done, does it mean that I have 80% chance of cancer? Because this test has an accuracy of 80%, right? So the test has an accuracy of 80%. I go get myself tested. It says you have cancer. I mean, it tested positive. Does it mean that I have 80% chance of cancer? Well, the answer is no. And that is where the Bayes rule comes in, right? The reason it is incorrect. The reason it is incorrect is because we have not incorporated the prior information. See, I went there and I got tested and it said you have 80%. I mean, the test has a accuracy of 80%. However, the base rate is pretty low, right? If I went there and you didn't get the test done, my probability of cancer would be 0.4%, 0.004. So which means that the actual value that you want is not this. It is this. All right. So in probability, when we will look at probability in this course, what you need to understand is how to convert things written in simple English into probabilistic notation. All right. So what I am asking here is not what is p of x equal to 1 given y equal to 1. What I am asking here is what is the probability of me having cancer given that I tested positive, right? So that's different, right? So we need one more information for that. Let's say we are also given the false positive rate for the test, which means what is the probability that the test would say positive when this person does not have cancer. So that is the false positive rate. Let's say it is 0.1, all right? So the way to compute this value is to apply the Bayes rule, all right? I've given you the equation for the Bayes rule over here. So when you go back, just sort of work through it, what you will see is that you have all these values, right? This is 0.8, this is 0.4, right? This, 0.004, this is the prior probability. This is again 0.8, this is 0.004. This is the false alarm rate, 0.1, and this is the probability of somebody not having cancer without knowing anything else. That essentially will be 1 minus py equal to 1, right? So when you put these all things in, you will get a different number. In fact, what you will get is I didn't get that sheet. Oh, yeah. What you will get is 0.031. That means that the probability of you having cancer, even though when you tested positive, is not 0.8, it's actually 0.031. And the reason is because you have to compute this probability, this conditional probability, which can be obtained by applying the Bayes rule. Any questions so far? All right. So these are pretty basic concepts. All right. We will later see how to use this Bayes rule for us, right? So for example, if you think of classification, right, like in neural networks, classification can be thought of as computing this conditional probability, which is what is the probability of my label, right, my y, to be one of the classes? What is the probability of this patient to be, this tumor to be benign, given I have seen the data for that, right? So we need to compute these things, all right? And typically what happens is that we can learn these quantities from the training data. So we can learn, okay, when the class is 1 or when the class is benign, what is the probability for any x, right? We learn this from the training data and then we apply the Bayes rule to compute this value, right? So when we see naive Bayes classification and maybe Bayesian networks, then we will see that this is essentially what it does. So this is a probabilistic notion of classification. So far, what we saw in neural networks and perceptrons was a functional form of classification, where we were trying to say what is f of x. Now here we are trying to compute these posterior probabilities. Any questions so far?